Looking at problem 65. Methanol has been suggested as an alternative to gasoline in an automotive fuel. Write a balanced chemical equation for its complete combustion. All right, so the complete combustion of methanol is like this, and we need to balance this. Carbons are balanced. Hydrogens, we have 4 here, so we're going to need 2 water molecules. Let's see, what else do we need to do here? We have 1, 2, 3, 4 oxygens, 1, 2, 3, so we're going to need 1 more oxygen, which would be 1.5 here. So if we have 2 here, 3, 2, and 4, then that would be a balanced equation. And that's 665. So we have 2, 3, 2, and 4. Okay, good. 667. Write the balanced chemical equation for the combustion of dimethyl sulfide in abundant supply of oxygen, CH3,2S. Whoops. CH3, that's the methyl group, 2 sulfide. All right, so combustion, combining with oxygen to form carbon dioxide, water, and sulfur dioxide, SO2. All right. You can see this. What page is this on? 237. All right. So when we have sulfur in compounds, we get sulfur dioxide. And this is a pollutant which can ultimately result in sulfurous acid when it's combined with water in the atmosphere. So this is a problem, sulfuric acid as well. And this is why you want to make sure you don't have any sulfur as a contaminant in your automotive fuels or any fuels that you're going to be burning, because this will produce acid rain. Okay, so we're going to balance this then. We can balance these by inspection. We have 2 carbons, 1 sulfur, 1 sulfur, 6 hydrogen. So we're going to need to put a 3 here, so we have 6 hydrogen on the right. Oxygens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to need 4.5 here, or 9. So 2, 9, 4. The water is going to be 6, and the sulfur dioxide is going to be 2. So 2, 9, 4, 6, 2. That should be our answer for 667. 2, 9, 4, 6, 2. Okay, those are the coefficients, right? 2 for the dimethyl sulfide, 9 for the oxygen, 4 for the carbon dioxide, 6 for the water, and 2 for the sulfur dioxide. 669. All right. Write the chemical equations for the reaction of oxygen with zinc, aluminum, magnesium, and iron to form iron 3 oxide. Okay, so zinc plus oxygen. The products here are going to be zinc oxide, right? And so we need to balance this chemical equation. You can also generally do these with inspection as well, but you always want to be sure that your electrons are balanced, right? That's the ion-electron method is for. And you can use the ion-electron method, which means take the half reactions and balance them individually. But generally, these ones also can be balanced with inspection. Okay, so you just have to make sure that the electrons work out. All right, so the zinc here goes to zinc oxide. We have our chemical equation. It's balanced here in terms of the elements, but we want to remember that the oxidation number here is 0. The oxidation number here is, oh sorry, it's not ZnO2, it's ZnO. So let's balance this chemical equation by putting a 2 here and a 2 there. All right, so now elements are all balanced, and we're going to verify here the oxidation state of the zinc. We're going to verify the electrons. The oxidation state of the zinc is 0. The oxidation state of the oxygen is 0. The oxidation state of the zinc here is +2, and the oxidation state of the oxygen here is -2. All right, so we had 2 oxygens gaining 2 electrons. So that's 4 electrons, right? 2 oxygens gain 2 electrons, that's 4 electrons. And then 2 zinc giving up 2 electrons, so that's 4 electrons as well. So electrons are balanced as well. All right, there's our zinc, aluminum, magnesium, and iron going to iron 3. All right, so aluminum's next. Aluminum plus oxygen is going to form Al2O3, oxygen gas, whoops, oxygen gas there. So we're going to need 2 aluminums, and we're going to need a 2 here and a 3 here, right? And then if we do that, we're going to need a 4 here. So again, we're just balancing by inspection, but in the end, we can look and see that the aluminum had a 0 charge, and here it has a +3 charge. So there were 4 aluminums that, and 4 here, that went from 0 to +3. 0 to +3, that's 3 times 4, that's 12 electrons that were given up by the aluminum. The oxygen went from 0 to -2, and there were 6 oxygens that did that, and we ended up 6 oxygens giving up, or gaining 2 electrons. 6 oxygens gaining 2 electrons, that's 12 electrons that were gained. So there's 12 electrons given up by the aluminum, and 12 electrons gained by the oxygen. So again, we see that balancing by inspection is fine, and we can verify that by looking at the electrons. Magnesium plus oxygen to form magnesium oxide. All right. So here we're going to need 2 here, 2 here, and that's balanced. All right. Again, we can do the electrons to verify, but we can see here that magnesium gained 2 electrons. That's 4 electrons. Magnesium gave up 2 electrons, and there's 2 of them, so that's 4. Oxygen, each one gained 2 electrons, and that's 4 there as well. So Fe plus oxygen going to Fe2O3, iron 3 oxide, right? And we have to balance this one. We can do the irons just first, and then we're going to have to change that in a second. But for the irons first, we're going to need a 3 here, a 2 here for the oxygens. So then this is going to need to go to 4. All right, so again, 4 irons went to +3. That's the oxidation state of that iron there. That's a total of 12 electrons. 3 oxygen went to -2. No, 6 oxygens, sorry, went to -2, and that's 12 electrons. All right, 669 is done. 671. Iodate ion reacts with sulfite ion to give the sulfate ion and iodide ion. Write a balanced net ionic equation for the reaction. Iodate ion. IO3 minus is the iodate. Iodate ion reacts with sulfite, SO sulfates, SO3 2 minus, to produce sulfate and iodide. SO4 2 minus and iodide ion. I minus. Right, a balanced net ionic equation for the reaction. Okay? So, and then so we need to balance this chemical equation, and we're going to do that using the ion electron method here. We need 3 waters over here, 6 protons over here. Okay, and let's see, 6 protons over here. Charges, we have 1 minus here, so we're going to need 6 electrons to the left as well. All right, for the sulfite to the sulfate. Sulfurs are balanced. Oxygen, we need 1 more oxygen over here. We're going to need 2 protons over here, and we're going to need 2 minus 2 minus 2 electrons over here. This is going to be multiplied by 3. So the electrons and the protons, oh, not 2 H2s, sorry, 2 H pluses. So the electrons are going to drop out, There's going to be 6 protons. 6 protons, they're going to drop out. So I'm just going to put the iodate here, plus 3 waters, plus a sulfite, yielding iodide ion, 3 waters also, 3 sulfates, SO4 2 minus. Oh, so this 3 needs to go with this sulfide too. I forgot that 3 there. So 3 sulfates, and then 6 protons and 6 electrons, which are going to drop out. So the waters drop out as well. 3 waters on each side. So we have the iodate, 3 sulfites, iodide, and 3 sulfates. Okay, so that should be the first part of 671. We have coefficients 1, 3, 1, 3, 671. All right, that's right. And now we're looking for, whoops, we need to keep those coefficients because we need to answer the next part, which requires the understanding of the stoichiometry. All right. So here's our balanced chemical equation down below here. And now the question is, how many grams of sodium sulfite are needed to react with 5 grams of sodium iodate? So if I have 5 grams of sodium iodate, IO3, all right, how many grams of, what is it, sodium sulfite? Where are we at? 671. Sodium sulfite. How many grams of Na2SO3, sodium sulfite, okay? Well, we can convert this to moles. How many grams of NaIO3? So what we need to find here is the molar mass of sodium iodate. We need to know how many moles of, for every 1 mole of NaIO3, how many grams of NaIO3, right? And it looks like it's 149.89 grams for every mole. And then we can see that the molar ratio is for every 1 mole of this stuff, we're going to need 3 moles, or be able to consume 3 moles of that stuff. So this is the IO3 minus, and this is the SO3 2 minus. Okay? And I kind of left out one slice here that I could include. For every 1 mole of NaIO3, I get 1 mole of IO3, right? So now I'm in moles of IO3. And for every 1 mole of IO3, I consume 3 moles of SO3 2 minus, and a similar slice that I would usually not include, but for every 1 mole of SO3 2 minus, that's 1 mole of Na2SO3 2 minus, or SO3, Na2SO3, and then how many, for every 1 mole of Na2SO3, how many grams of Na2SO3 will that be? All right, so now we need to know the molar mass of sodium sulfite. Okay, so after we get the molar mass of sodium sulfite here, 126.043 grams of sodium sulfite for every mole of sodium sulfite. Then we should be able to answer the question here about how many grams of sodium sulfite we'll need. Okay, so we have 5 divided by 149.89 times 3 times 126.043. So I'm looking at 12.6. How many significant figures? 12.6 grams. sodium sulfite. So that's 671. Oh! What happened? You didn't get the right value. 12.6 grams of sodium sulfite. Let's see. All right, so we're double checking here the molar mass of sodium sulfite. (126.043), 5 grams of sodium iodate, Let's double check that one. Molar mass of sodium iodate. Oh, yeah. This one's not right. Sorry about that. I chose the wrong one. It's 197.89. That's sodium iodate. This was sodium iodide. Wasn't clear enough when I pronounced that. So 5 divided by 197.89 times 3 times 126.043. All right, so not 12.6, but 9.55. See what we got here, 671, 9.55. All right, 673. How many grams of copper must react to displace 12 grams of silver from a solution of silver nitrate? So I have a solution of silver nitrate. How many grams of copper? What? 12 grams of silver. So I have 12 grams of silver. And I want to know grams of copper. So I have 12 grams of silver, and I want to know 12 grams of copper. And this reaction is between the silver ion and the copper, right? So the silver ion is higher in the activity layer, is less active, right? So it's going to remove electrons from copper. So this is going to be Ag0, and this is going to be Cu plus 2. All right, so we see that we're going to need to have 2 silver ions for every 1 copper ion, right? To make sure that those charges balance, right? So this one, you can't balance simply by balancing the atoms. You need to make sure the electrons are balanced, right? And if you didn't understand that, you can just follow the ion-electron method, where we take Ag going to Ag0, Ag plus going to Ag0, and we see that we have 1 electron combining with Ag to form Ag plus. And the other half reaction is copper going to copper plus 2, and that means we need to have 2 electrons let go. So therefore, we're going to have to multiply this silver 1 by 2. Okay? All right, so if we have 12 grams of copper, 12 grams of silver, what's the molar mass of silver? Ag, 107.87. 107.87 grams of silver for every 1 mole of silver, right? And there's 2 moles of silver consumed by every 1 mole of copper consumed. And for every 1 mole of copper, how many grams of copper are there? Copper is 63.55 grams of copper for every mole of copper. So this should tell us how many grams of copper are required. So we have 12 divided by 107.87 divided by 2 times 63.55. So that's 3.53 grams of copper. So let's verify. 673, 3.53. Okay. 675 now. In an acidic solution, permanganate ion reacts with tin 2 ion to give manganese 2 ion and tin 4. So we have Sn plus 2 going to Sn plus 4, and the Mn, what's the manganate ion? What's the other product? Manganese plus 2. And this is the MnO4 minus ion. Permanganate, tin 2, tin 4, manganese ion, manganese 2 ion. In acidic solution, that occurs. Double check. Tin plus 2, permanganate, MnO4 minus, manganese, and tin 4. Write a balanced net ionic equation for the reaction. All right, so we have tin 2 going to tin 4. Here's one of our half reactions. We see that we need 2 electrons on the more positive side, right? That one's done. The MnO4 minus going to Mn plus 2. All right, we need to just balance oxygens here by adding 4 waters, 8 protons over here, and now we need electrons over here. We're going to need 6 electrons. 6 electrons on the left. That'll end up with 5 electrons, because this is a negative charge. Wait, hold on a second. So, yes, because now the net charge over here is 8 plus, 5 minus, plus 3, minus 1, plus 2. And over here we have a plus 2 net charge as well. Okay, so that is the equation. Ooh, that looks cloudy. Is that right? Double check this one. MnO4 minus, Mn plus 2, right? So we need 4 waters on the right, MnO4. That's 8 protons on the left now. The charges, again, initially this is a plus 2 side over here, and this is a plus 7 side over here. Oh, sorry, plus 2 side over here, plus 7, so we need 5 electrons. Okay, double checked it, it looks okay. So we're going to multiply this one by 2 and this one by 5. So we get rid of our 10 electrons. So that's going to be 5 Sn. Write this a little bit higher because it looks like we're probably going to do some math with it, calculations a little bit later. So 5 Sn plus 2s plus 10 electrons, 16 H pluses, plus 2 MnO4 minuses, yielding 5 Sn plus 4s, 5 Sn plus 4s, 10 electrons, 2 Mn plus 2 ions, and 8 H2O molecules. Okay, so anything else that can cancel out? Doesn't look like it. Looks like we got everything done there. So hopefully we got that right. 675. Now, how many milliliters of 0.23 molar potassium permanganate solution are required to react completely with 40 milliliters of 0.25 molar tin chloride? So if we have 40 milliliters of, well, let's start off there. Well, that's fine. 40 milliliters. We're going to change that to liters, though. 0.04 liters of 0.250 moles per liter tin SnCl2. How many milliliters of that permanganate for 0.25 molar tin chloride solution? All right, so now we're in moles of tin chloride. And for every 1 mole of tin chloride, there's 1 mole of tin. I'm not going to include that in here, but we can see that. For every 1 mole of tin chloride, there's 1 mole of tin. And for every 1 mole, every 5 moles of tin plus 2 MnO4 minus ions are consumed. So 2 moles of permanganate ions are consumed. And the question we want to be in here, or the answer we want to have, is milliliters of the KMnO4 solution, right? So we need to see how many moles of the potassium permanganate solution we need. This is in moles of permanganate, and that's also the same as moles of potassium permanganate solution, because for every 1 mole of potassium permanganate, you have 1 mole of the permanganate ion. Okay? So we don't need to take this to potassium permanganate. They're not asking for grams of potassium permanganate. They're asking for milliliters of solution. So for every, there's 0.230 moles of MnO4 minus for every 1 liter of solution. All right? And now we're in liters of the permanganate solution. And for every 1 liter, there's 1,000 milliliters. Okay, so we just multiply by 1,000 here to get it into milliliters. All right, so we got 0.04 times 0.25 times 2 divided by 5 divided by 0.23 times 1,000. So 17 point, how many significant figures? 3? 17.39 milliliters of potassium permanganate solution. 6.75. Okay, so looks like we got it. Higher, they only have 2 significant figures. $17.4. Why do they only have 2 significant figures? 40.0. They should have 3 significant figures. So that looks like a little error in the book, but not a very bad one. Okay. 677.